Calculus, video 53, optimization, example 2. In this example, we would like to determine the coordinates on the curve y equals the square root of x plus 3 that has a minimum distance from the point 5, 0. Okay, so start off by asking yourself, what are we trying to minimize or maximize? In this case, we're trying to minimize the distance. So we want to create an equation that involves the distance. Right? That's the thing we're trying to maximize or minimize. That is the event that's occurring. We need an equation that describes that event. Okay, so we're going to create some sort of a distance equation. And then we'd like to minimize it. All right, so we have the curve y equals the square root of x plus 3. Let's take a quick picture there. Y equals the square root of x plus 3. That means we're moving to the left by 3, having a nice square root, some function that looks kind of like that. And we have the point 5, 0. 5, 0 is going to be somewhere about right here. What we know, or maybe we don't know, but we will know, is that we want to minimize the distance between the curve and the point. There is some point on the curve, I'd say it's about right here. There's some point on that curve, some point x, y on that curve, so that the distance between the curve at that point and 5, 0 is the is the minimum. So this is the distance d. Okay, and we're trying to minimize that distance. What point xy creates a minimum distance in that line segment? What we'll see, and not really see here in this particular class, but maybe intuitively see, is that the line segment that connects that for the minimum distance will meet that curve at a right angle. That's not so much important to this particular problem, but it does come back later on, that where that minimum distance meets forms a right angle with the curve. Okay, so we want to minimize the distance, so maybe we can use the distance formula. All right, the distance formula is the square root of the distance between the x values, x minus x1 squared, plus the distance between the y values, y minus y1 squared. We want to minimize this. Okay, we see a couple of things here. We have the square root of the x minus x1 squared plus y minus y1 squared. There are two variables on the right hand side here. The variable x, we're not sure exactly where x is on this curve, so that is a variable. The variable y, we're not sure where the y value is on that curve, so that's a variable. The x1, y1 would be the point 5, 0. Right, so the 5, 0 is acting as our x1, y1. So that is a constant. That one is not moving. So here's what we can say. The distance that we're trying to minimize is equal to the square root of x minus 5 squared plus y minus 0 squared. Or perhaps more accurately, distance is equal to the square root of x, not more accurately, but more simplified, the square root of x minus 5 squared plus y squared. Okay, so we're trying to minimize this distance, but we still have two variables here. We still have an x and we have a y. So we need an equation that will relate x and y together so that we only have one variable on the right-hand side. What should that be? Well, the thing that relates x and y is the equation of the curve. Y is equal to the square root of x plus 3. And if y is equal to the square root of x plus 3, we actually have a y squared over here, so let's replace that and say that y squared then is simply x plus 3. Okay, like this. So the distance is equal to the square root of x minus 5 squared plus y squared, which is just x plus 3. All right, we now have, fairly quickly in this case, a distance formula involving just one variable, and we can now take the derivative and find out when it's equal to 0 or undefined. We could do it from right here. We could. But let's think about this idea. The distance is the square root of this x minus 5 squared plus x plus 3. Instead of having that square root, because then the idea here I'm trying to get at is what we have now is we have the x minus 5 squared plus x plus 3, which we can multiply out all to the 1/2 power. If I take the derivative, I have to take the 1/2 times the thing to the negative 1/2 times the derivative of the inside, and it gets kind of messy, right? So what I want to do instead is think about this. This distance will be minimized. This distance will be minimized whenever the inside of the square root is minimized. Okay? The distance will be minimized whenever the inside of the square root is minimized. In other words, if the inside of the square root is 9 versus if the inside of the square root is 4, 9 is larger than 4, and the square root of 9 is 3, the square root of 4 is 2, 3 is larger than 2. Not the same amount of largeness, but by making the inside smaller, the square root also becomes smaller. The smaller the inside, the smaller the overall thing. So it's enough to minimize the inside of the square root. At that same point will be the minimize of the entire distance d, the square root of the whole thing. So what we're saying is we don't have to do this whole square root part. All we have to do is minimize what is inside here. If we minimize what is in orange here, we will also minimize the square root of that. So I'm going to call a new distance d and say let d equal not the square root of it, but just the x minus 5 squared plus x plus 3. And I want to minimize d, capital D. Because if I minimize capital D, I will have also minimized lowercase d, which is the square root of this. Okay, but this is a little bit easier problem to work with. So simplifying here, let's move to not orange. D is equal to x minus 5 squared is x squared minus 10x plus 25. That's x minus 5 times x minus 5 plus x plus 3. That means d is equal to x squared minus 9x plus 28. Okay, so the derivative will be d prime is equal to 2x minus 9. We are looking for whenever the derivative is equal to 0 or whenever the derivative is undefined. It is never undefined because the derivative is a line. It is equal to 0 anytime 2x minus 9 is equal to 0, 2x equals 9, x equals 4.5. So we will get a minimum distance whenever x is 4.5. Okay, well, if x is 4.5, what is the y value? So you're picturing, that looks about right, kind of how I've drawn it up here. The x value is 4.5. Let's find the y value by plugging 4.5 in for the x in the y equals square root of x plus 3. So x is 4.5, y equals square root of x plus 3. Therefore, y equals the square root of 4.5 plus 3. That's the square root of 7.5. I'll just leave it like that. And so the coordinates that minimize the distance, the coordinates on the curve, the coordinates on the curve y equals square root of x plus 3 that minimize the distance to the point 5, 0. Are 4.5 for the x, square root 7.5 for the y. And that's it.